This is the 1991 free response for intermolecular forces. If you have not already done this problem, please pause or stop this video and go back and do it yourself. You're not going to help yourself if you just watch me do it. You should do it on your own and then come back and see where you could have possibly gotten some additional points. All right? So right off the bat, when we get this problem, first thing we see is this huge table. It says table 1, and it gives us melting points and conductivity. So what do we know about melting points? Well, we know that melting points are directly proportional with the intermolecular forces of that compound involved. So we're going to have to talk about intermolecular forces at some point to do with that. Conductivity. What's the big buzzword with conductivity? Well, in order for something to conduct electricity, the electrons of that electricity have to be able to be carried by some sort of mobile charged ion. So some sort of metal usually carries it. Right? So magnesium being an example, because I know we have to use it later, or beryllium. So that was another one that they gave us. All right? One of these ions is going to have to carry that electron to complete a circuit and conduct electricity. So mobile charged ions, that's going to be one of our buzzwords. We're going to have to talk about intermolecular forces. Next thing, table 2 is bond length. Okay, so what do I know about bond lengths? Well, I know that shorter, can't spell today, shorter equals stronger. The closer the two nuclei can get to one another, the stronger that bond is. So ions are huge anions, itty bitty cations. All right, but I don't have anything here that are ionic compounds. All these are covalent compounds. So what do I know about covalent compounds in bond length? Well, I know that a single bond is a pretty long bond length, because that's the weakest, right? If you're playing Red Rover, one person holding one person's other hand, that one hand is not that strong. But if they hold two hands, they're going to be pretty strong. They're going to be pretty close together. And if they hold two hands and a foot, they're really close together. So triple bonds are going to be our strong suit, and single bonds are going to be our weak one. Okay, so now let's look at the problem. What does it say? It says account for the differences in the properties given in tables 1 and 2 in terms of differences in structure and bonding. So we're going to have to talk about structure and bonding. And it says properties. So we're going to need to talk about more than just one of the properties. We've got to talk about both if we're talking from table 1. And we've got to talk about bond length as much as we can get from table 2 if we have to talk about it. For each of the following pairs. So now we look and, oh look, they're all paired up nice and neat. So I'm going to scroll this down a little bit. Okay. So magnesium chloride and silicone tetrachloride. What do I know about these two? Well, magnesium chloride, magnesium's a metal. Chlorine is a nonmetal. So I've got a metal and a nonmetal. Silicone is a metalloid. And let's just call it a nonmetal for right now, because it doesn't conduct electricity too well. Chlorine is a nonmetal, so I've got two nonmetals together. What is that? Ah, it's a covalent bond. So silicone tetrachloride is covalent. All right, and magnesium chloride, if I have a metal and nonmetal, that's an ionic bond. All right, so there we go. I've pointed out the differences in their bonding. Check. So what are their differences in properties? All right, so let's go with these properties from table 1. Magnesium chloride, melting point is 714 degrees Celsius. That's pretty hot. Melting point for silicone tetrachloride is pretty low. Okay, so now I got to account for that. And we know it has to do with the intermolecular forces. So which one do you want to tackle first? Let's tackle silicone tetrachloride. Silicone tetrachloride's intermolecular forces are London dispersion forces and are weak, right? Because there's a lower melting point. So they must be weaker than the intermolecular forces holding magnesium chloride together. All right, so now we got to talk about what's holding magnesium chloride together. Well, magnesium chloride is a lattice structure of magnesium being positive, surrounded by chlorines, which are surrounded, not chlorine, but of anions, which are surrounded by more magnesiums, which are surrounded by chlorines. So we have this electrostatic forces. Hold magnesium chloride in a lattice structure. So in order to melt magnesium chloride, you've got to break those bonds holding it together to separate these two apart. So any attempt, so we're going to have to overcome in order to melt magnesium chloride, you must overcome its electrostatic forces. Okay? So that handles the melting point. Before I move on, let me just double check, make sure I have things that make sense. So silicone tetrachloride is covalent. Its intermolecular forces are, I want to put its intermolecular forces are London dispersion forces and are weaker than the intermolecular forces holding magnesium chloride together. Wait a minute. Magnesium chloride isn't a molecule, so it can't be intermolecular. It must be something else. Let's get rid of that. Are weaker than, we could say electrostatic forces. We could say the attraction. I realize that's hard to read, but you'll figure it out. Holding magnesium chloride in a solid state. Electrostatic forces holding magnesium chloride in a lattice structure. In order to melt magnesium chloride, you must overcome its electrostatic forces. Okay, that makes a decent amount of sense. So now, why does magnesium chloride conduct electricity in a molten state? Well, magnesium chloride in a molten state has mobile and charged scroll down a little bit more. Ions that can conduct electricity while silicone tetrachloride in its molten state not. All right, did I answer that question? Yes, and I think we're good. So now we just got to go back and see how many points. This question's worth 3 possible points. You got 1 point for pointing out that silicone tetrachloride is covalent and magnesium chloride is ionic. You got 1 point for pointing out that silicone tetrachloride has London dispersion forces, while magnesium chloride has electrostatic forces, and relating that somehow to the energy it takes to melt it. So that would be like this whole paragraph here. Lastly, the third point comes from pointing out that magnesium chloride has mobile and charged ions that can conduct electricity, and silicone tetrachloride does not. So next they want us, okay, big shot, you've pointed out the difference between an ionic and a covalent bond. But what about between two that are relatively similar. What about something that has something in common? So point out the difference now between magnesium chloride and magnesium fluoride. Well, what's the difference there? Well, they both contain magnesium, so we're probably not going to get a big difference from that. This has chlorine, and this has fluorine. So what's the difference between chlorine and fluorine? Well, they're both 1 minus, so it can't be that. Can't be dealing with that. It has to do with something else. Well, what do we know about chlorine and fluorine? Fluorine, if you were to draw fluorine, just the atom, you'd have 2 valence shells. If you drew chlorine, you'd have 1, 2, 3 valence shells. So that'd be its, maybe it's the size. Oh, wait a minute, I know something about this. The strength of an ionic bond, the forces, those electrostatic forces, are proportional to the charge of the first ion times the charge of the second, divided by the distance between them squared. So the difference here is this distance. Fluorine being so much smaller, those 2 nuclei must be getting very close together. So that's why this is stronger than the other ones. Now I got to relate that to my grader so that they know that I know what I'm talking about. So let's start by reconfirming what we know. We know that magnesium chloride has a lower melting point than magnesium fluoride because the fluoride ion is much, well, we don't know if it's much because I'm not a particle physicist, is, let's just say, smaller than the chloride ion. Ionic bond strength how I want to say this. Is proportional to electrostatic forces holding one ion to another. And I might even write this formula, because this is what I'm basing this off of, so I might as well write it down here for my grader so they know that I know it's a coulombic force dealing with the distance between the 2. Since fluorine is smaller, its radius value is less, and therefore its force is greater, resulting in a higher melting point. Whew. This question was worth 2 points. I need my highlighter. Question was worth 2 points. You got 1 point for pointing out that fluorine is smaller than chlorine. Fluoride is smaller than chloride. And 1 point for pointing out that because it is smaller, the distance between the 2 ions is less and the bond is stronger, and therefore you have a higher melting point. You could have gone about saying that in many different ways. I like this formula personally, just because it sums up all you need to know, and it's a great explanation. It's easy to get all of that out. So our next 2 problems deal with table 2. So let's go back up and look at table 2. We're going to look at the difference between fluorine and bromine to start with. So the difference here, fluorine has got a short bond length in comparison to bromine. So now we got to figure out why. Okay, so, well, we know it's something to do with double, single, or triple, so let's try the Lewis structures. Lewis structure of fluorine looks something like that. Bromine Okay, well that didn't help me at all. Okay, so what else do I know? Well, we just talked about the distance here. So fluorine, very small. Let's look at bromine. Bromine, 1, 2, 3, 4 shells around that nuclei. So bromine, ooh, is pretty much bigger, much bigger. So that must be the difference. These two nuclei for bromine must not be able to get very close together because they have so many valence shells around them. So now we just got to relate that to our grader. Okay. The fluoride atom is smaller than the bromide atom. Sorry, the bromine atom. And therefore, fluoride nuclei can attract other electrons more since it is shielded less. Therefore, bond length is shorter. All right, so let's talk about points. This question was worth 1 point. And that point is simply for saying fluorine is smaller than bromine. So yes, I went and talked about more than I needed to, but at least I know it's true. Maybe it will help me in the next question. So the next question says, point out the difference between fluorine and nitrogen. Why is the bond length of nitrogen shorter than fluorine if fluorine is so small? Well, for this one, I'm not going to go back up, but let's look at the Lewis structures again. So fluorine looks like this, we said. Nitrogen, do the Lewis structure, it's triple bonded. So that explains why it's a shorter bond. Triple bonds are much closer together. So fluorine has only one area of electron density between its nuclei. Yeah, I can't stop. Close enough. Between its nuclei. While nitrogen has 3 areas of electron density to attract its nuclei closer together and decrease the bond length. All right, this last question was worth a possible 2 points. One of those points was simply for pointing out that one is single bound and one is double bound. And the last point was for pointing out that single bonds are longer than triple bonds. In fact, you really didn't even have to go into areas of electron density. You just had to say longer, shorter, done. So that is the total 8 points possible for this question. 2 plus 1 is 3, plus 2 is 5, plus 3 is 8. So remember, a score of 4 out of those possible 8 is a really decent and good score. So don't beat yourself up too much if you did not get all the points possible for each question. If you got 4 of them, you are well on your way to that 3, 4, or 5.